Hi, good evening. Welcome to ACE Online. Today, I am going to discuss one of the important concepts from the material science, especially for GATE and AC. From this concept, every year there will be a question, okay, for GATE and for ESC. Maybe for ESC, there may be more than one question. For GATE, every year there is one question from this concept. Not only GATE and ESC, but also other competitive exams like BARC, ISRO, DRDO, state service exams and railways. In every competitive exam, there must be a question from this concept. That concept is actually iron-cementite phase diagram, iron-cementite equilibrium phase diagram. Generally, there are three types of phase diagrams, especially binary phase diagrams. One is isomorphous phase diagram, second is eutectic phase diagram, third is type 3 phase diagram. But here, out of these three types of phase diagrams, okay, the eutectic phase diagram, and within the eutectic phase diagram, this iron-cementite phase diagram is very, very important. That's why I selected this topic to explain here. Now, myself, Vagula Madhu Sekhar, I did my MTech from IIT Roorkee with Industrial Engineering as a specialization. I'm the faculty of ACE Engineering Academy from last 8 years. Okay. Now, the first question, most of you people are in doubt like, is it steel and iron are same? Is it steel and iron are same? If it is not, what is steel, what is iron? How will you get a steel, how will you make a steel, or how will you make a iron? That is a question main, okay. I think some of you people are thinking that steel and iron both are same like that, but I am saying that steel and iron both are not same, okay. Remember, steel and iron both are not same, okay. Steel is an alloy, iron is a metal or element, okay. Steel is an alloy of, okay, steel is an alloy of iron and carbon. Steel is an alloy of iron and carbon. But iron is a metal, but iron is a metal or an element, we can say. Iron is a metal or an element, right. So how can we make a steel from iron? That is one doubt. Second doubt, first of all, will you get iron directly from the earth? That is, most of you people think that iron you will get directly from the earth, and by adding carbon to the iron we are making steel like that, most of you people are thinking, but it's not correct. You won't get pure form of iron from the ground. You won't get pure form of iron from the ground. What you will get, listen, what you will get actually, you will get from the ground, okay, listen carefully, from the ground you will get, from the earth otherwise from the ground, okay, from earth or from ground you will get iron in the form of, you will get iron in the form of iron ore. You will get iron in the form of iron ore, right. So what is an iron ore? First of all, what is an iron ore? What is an iron ore? Iron ore is nothing but, iron ore is nothing but iron oxide Fe2O3 or Fe3O4. Iron is present in the form of oxygen, in the form of oxide, that is iron oxide. Not only this iron oxide, but also the iron ore consists of large amount of sand. Not only this iron oxide, but also consists of large amount of sand. Sand is nothing but silica, SiO2. Remember, sand is nothing but silica, SiO2. And not only sand, but also so many other elements, like okay, so many other elements like let us say chromium, manganese, okay, chromium, manganese, tungsten, okay, carbon, like that, so many elements are there. This is an iron ore actually, okay. So, you won't get iron, pure form of iron directly from the earth. You will get iron in the form of iron oxide. Not only iron oxide, but also sand and other elements are present in the iron ore. What are the different iron ores? What are the different iron ores we are familiar about? What are the different iron ores? Do you know? One is magnetite. One is magnetite. In this magnetite, okay, remember, in this magnetite, large amount of iron is present. Let us say 70% of iron. If you consider magnetite iron ore, in that 70% of iron and some 25% of sand, 25% of sand, okay, and 5% of other elements. 5% of other elements present. Okay, this is magnetite. Okay, this is actually a magnetite. And the second form of iron ore is hematite. Second form of iron ore is hematite. Okay, in this hematite iron ore, 60% of iron is present. 60% of iron, some 30% of sand and other elements are present. And the third one is limonite. Limonite. Okay. Here some 50% of iron is present. Some 50% of iron is present. Okay. This is actually iron ores, different iron ores, but in India we have large quantity of hematite. Okay. We don't have magnetite much, we are having only hematite, right. So, these are the iron ores. From these iron ores we are making iron, we are making actually pure form of iron, we can say pig iron we are making by using a blast furnace, okay, by using a blast furnace operation, okay. So, we are collecting this iron ore and we are also collecting like limestone, that is calcium carbonate, and coke coal, anthracite we are making. We are making coke coal from the anthracite, we are producing coke coal from the anthracite. I will give you that one. First we should prepare a mixer, after that we should go for blast furnace, okay. Listen here. First we should prepare, okay, mixer. Before going to the blast furnace operation, we should prepare a mixer. Remember, we should prepare a mixer. That mixer consists of, remember, we should prepare a mixer. That mixer consists of, remember, iron ore. That mixer consists of iron ore plus limestone plus coke coal. See, listen, iron ore, limestone is nothing but a calcium carbonate. Limestone is nothing but a calcium carbonate. Coke coal is nothing but a carbon. Now, this is a mixer. First we should prepare a mixer before going to do the blast furnace operation, okay. Before going to do the blast furnace operation, first we should prepare a mixer. Then what we are doing, we are sending this mixer to the top of the blast furnace, and from the top of the blast furnace we are releasing this mixer, and from the blast furnace we are producing a pig iron. Now see here, let us see a small video clip here I am giving. Okay, from this video clip you will understand how can we produce a pig iron from the iron ore. Now this is iron ore. In this iron ore there are so many elements like chromium, manganese, iron oxide, like that. This is a earth ground level, right. Now here this is a blast furnace, and this is a mixer. These trolleys are bringing this mixer towards the top of the blast furnace, and this mixer is released from the top of the blast furnace. Okay, this mixer is released from the top of the blast furnace. Now see here. Now this is a blast furnace working temperature, that is approximately 2000 degrees Celsius. Okay, we are heating that mixer up to 2000 degrees Celsius by, and the dimensions of the blast furnace approximately it is given, and how it is going to react the iron oxide with the calcium carbon monoxide. Now see here, from the iron oxide, oxygen atoms are connected with bonded with the carbon and form iron, pure form of iron. Now see here, in this video clip we are mixing the mixer of coal and iron ore and also coke coal, and we are sending to the top of the blast furnace here. This is a mixer actually, this mixing, we are mixing here from this. And this is actually a turbine wheel. So from this turbine wheel we are sending a hot air into the blast furnace actually. We are generating we are producing a hot air by using this turbine wheel and a cam and follower. Then we are heating the mixer in the blast furnace. Now by sending oxygen and coal is there, so it form a carbon dioxide and carbon monoxide, and this carbon monoxide react with iron oxide and form iron. Carbon monoxide react with iron and form iron. See here, this is the blast furnace operation now. See here, this is a mixer. We are heating that mixer and it converted into liquid state. Okay. In the liquid state, after reacting with iron, there is a slag formation. Okay. Calcium silicate, a slag is formed. The slag is collected in the right side, and pure pig iron is collected on the right side. Slag is collected on the left side and pig iron is collected on the right side. Now see here, listen carefully here, the iron ore, that is nothing but iron oxide react with the carbon monoxide, form iron and carbon dioxide, and this carbon dioxide react with the calcium carbonate and also silica, that is SiO2, calcium silicate. Remember, calcium silicate CaSiO3, okay, CaSiO3, that is nothing but a calcium silicate, that is a slag, okay, and the density of the slag is much lesser than the density of pig iron. The density of slag is much lesser than the density of pig iron. Because of the density difference, we are removing the slag from the pig iron easily. We are removing the slag from the pig iron easily. So from the blast furnace, what we are producing? From the blast furnace, we are producing pig iron. Understand? So what is this pig iron? Pig iron is nothing but a molten state of iron, okay, liquid state of iron, right? So what is this pig iron? What, from the blast furnace, what we removed from the iron ores? Let us consider here, okay, this is an iron ore. From the blast furnace, we removed this 25% of sand, but we didn't remove this chromium, manganese, tungsten, carbon like that, right? Iron is there, these 5% of other elements are there, that is nothing but a pig iron, okay na? So what do you mean by, listen carefully, what do you mean by pig iron? Listen, what do you mean by pig iron? Pig iron is nothing but, remember, what do you mean by pig iron? Pig iron is nothing but molten state of iron, okay. Pig iron is nothing but a molten state of iron. Pig iron is nothing but a molten state of iron, okay, molten state of iron that consists of, okay, that consists of 95% of pure iron and 95% of 5% of other elements, 5% of other elements. This is a pig iron, right. Now, from the pig iron, listen carefully, from the pig iron, we are producing different forms of materials. Okay. From the pig iron, we are producing different forms of materials. Let us consider one form of a material is wrought iron. One is wrought iron. Okay. Second one is steel. Second one is steel. And third one is cast iron. Okay, na? Remember, what is the base material to produce a steel and cast iron? That is nothing but a pig iron. Okay, what is the base material to produce a steel and cast iron? That is nothing but a pig iron. Pig iron is nothing but it is having some 95% of iron and 5% of other elements. Now, so what is wrought iron? Wrought iron is actually a pure form of iron. After removing other elements, it is a pure form of iron. It is a very good ductile material. Okay, but some small amount of silica slag is there, silicon is there. Okay, and this wrought iron is produced from a process called puddling process. You just remember the name. You no need to remember the production process of wrought iron because it is not that much important for your GATE and ESE, because actually the production of wrought iron most of us we learn from steel subject, steel making subject. It is not required actually here for you. Okay, wrought iron is a pure form of iron, remember. Next, steel is an iron carbon alloy. Cast iron is also an iron carbon alloy. Okay, the cast iron is produced from a cupola process or a cupola furnace. A cast iron is produced from a cupola furnace. Remember, this is also important for your exam objective type questions. They will ask you. Okay, cast iron metal is produced from the cupola furnace. What type of furnace we are using? Cupola. And for steel production point of view, there are so many methods are there, but I will give you some basic standard methods. If you want, you just remember those methods. One method is a Bessemer method. Bessemer method, we are producing a steel by using this Bessemer method, and in this method, okay, 2000 tons per hour we can produce. 2000 tons of steel per hour we can produce. Okay, now, and the second one is open hearth method. Open hearth method, Bessemer method, open hearth method, and arc electrode method, arc electrode method, and basic oxygen method, basic oxygen method. Okay, these are the different methods we are using to produce a steel. Right, now clearly understand. Now understand how can we make a steel from the iron. Actually, you won't get iron pure form of iron from the earth. You will get in the form of iron ore, and we purify that iron ore from the blast furnace, and we got a pig iron. From the pig iron, we are producing different forms of materials. Right. Okay. Now, here I am going to discuss about steel and cast iron elaborately by using this iron-cementite phase diagram. Okay, na? Now, in this iron-cementite phase diagram, the x-axis represent percentage of carbon and y-axis represent temperature. Okay, the x-axis represent percentage of carbon and y-axis represent temperature. Okay, and by cooling the liquid iron carbon alloy from the liquid state, we will get different phases of this iron carbon alloy. That's why it's a phase diagram. Okay, na? Equilibrium phase diagram. I'll explain this phase diagram one point to point. First I will explain about the x-axis. Let us consider this is also an same diagram but not visible, that is why I selected this one. Now let us consider first of all iron cementite phase diagram is what type of phase diagram. Okay. I said there are three types of binary phase diagrams. First of all, what do you mean by binary phase diagram? Binary phase diagram is nothing but, okay, the phase diagram is drawn by considering two elements. Okay. Let us take copper and nickel, lead and tin, iron and carbon, all these comes under this category. But again this binary phase diagrams are divided into three types based on solubility of these components. The first one is isomorphous phase diagram. What is that actually? The two components which are completely soluble in the liquid state and solid state. The example is copper nickel, that I am not explaining here. The second one is eutectic phase diagram, type 2 eutectic phase diagram. What is that actually? The two components which are completely soluble in the liquid state but partially soluble in the solid state. That means in the solid state the composition generate more than one phase. Okay. So the example for the eutectic phase diagram is lead and tin phase diagram and iron cementite phase diagram. Okay, now, so because see here in this diagram liquid, gamma iron, alpha iron, cementite, all these are phases in the solid state. So the material is not completely soluble in the solid state, that is why remember the iron cementite phase diagram is eutectic phase diagram. Okay, na? The iron cementite phase diagram is eutectic phase diagram because the two components, what are those two components? Iron and carbon, they are not soluble in the solid state. Next, what type of alloy is it is? What type of alloy is it is? Actually, there are two types of alloys or two types of solid solutions. You are familiar about these two types. One is a substitutional solid solution, second is interstitial solid solution. What is a substitutional solid solution? Here the solute atom is occupying in place of solvent atom, that is a substitutional solid solution. But interstitial solid solution means, interstitial alloy means the solute atom means what? What do you mean by solute atom? The low concentration material in an alloy is a solute. Okay. The solute atom is occupying at interstitial position. Now here what type of alloy we are discussing here? We are discussing here, okay, iron carbon alloy. We are adding carbon to the iron. The x-axis is percentage of carbon in iron, right? Now the size of the iron, the radius of iron is very large. The radius of iron is very large in compare with the radius of carbon. The radius of iron is very large in comparing with the carbon, so that the carbon atom is occupying at interstitial position. Let us say here, let us consider, see here, these are iron atoms. Okay. These are iron atoms. Okay. These are iron atoms. Now, if you add carbon to the iron, okay, the carbon atom is occupying at this interstitial space. Okay, at this interstitial space, this is carbon, this is carbon, this is carbon, this is iron, this is iron, this is iron. So the iron carbon alloy is an interstitial alloy. Remember what type of alloy this iron carbon alloy? it is an interstitial alloy. So, steel is what type of alloy? Interstitial alloy. Cast iron is what type of alloy? Interstitial alloy. Remember that. Next, another important point. The maximum interstitial space between two iron atoms that can fit an ideal carbon atom. Now listen carefully. At room temperature, okay, at room temperature, the crystal structure of iron is BCC. Okay. At room temperature, the crystal structure of iron is BCC. So, if we add carbon to the iron, where it is going to occupy at room temperature, where it is present the carbon atom? The carbon atom is present between the edges, because in a BCC structure, two corner atoms are not touching. This is a BCC structure. Remember, I will write here, that point I will write here, okay. At room temperature, okay, at room temperature, the structure of iron at room temperature, the structure of iron is BCC. At room temperature, the structure of iron is BCC. So, here I am considering the BCC structure. So, at every corner there is one atom, at the body center there is one atom. Here in BCC structure, all 8 corner atoms touch with the body center atom, but no two corner atoms are touching with each other. This is an iron atom, this is an iron atom, this is an iron atom, but between these two iron atoms there is a space. So, if we add carbon to the iron, okay, if we add carbon to the iron, the carbon atom is occupying like this here. The carbon atom is occupying like this here, like this here, like this here, here. At all edges based on the percentage of carbon, right. Now, my question is what, what is the maximum interstitial space? Interstitial space means what? Between the iron atoms, what is the space, maximum space? So, that space is useful to fit a carbon atom, right. So, the maximum interstitial space between two iron atoms, listen carefully, this is iron atom and this is also iron atom. Between these two, okay, the maximum interstitial space is this one, maximum interstitial space. Now, what is the total length of this actually? The total length of this is nothing but a lattice constant. I am assuming this lattice constant is A, lattice parameter, right. Now, the total length is A and this length is how much actually? This is the radius of iron atom and this length is how much? Radius of iron atom, right. So, total length is A and this is R and this is R. So, the maximum interstitial space, remember, maximum, okay, interstitial space, maximum interstitial space is equal to, okay, A minus 2 into R. A is a lattice constant, R is the radius of the iron atom. A is a lattice constant, R is the radius of iron atom. This is the answer. But for your exam point of view, sometimes they will ask you, okay, what is the maximum ideal radius of carbon or ideal radius of the atom that can fit between two iron atoms, and they will ask you. This represent actually a diameter of the ideal atom, but sometimes radius also they will ask you. If they will ask you the radius, listen carefully, radius of ideal carbon atom is A minus 2R by 2. Sometimes they will ask you in terms of A, or sometimes in terms of R also they will ask you. Now listen carefully. We know that for BCC structure, we know that 4R equal to root 3A. For BCC structure, we know that 4R equal to root 3A. It's a body diagonal by considering body diagonal. So, in case if they ask you in terms of A, you can also write this one like this, A minus root 3A by 2. This is also correct, right? A minus root 3A by 2, this is also correct, right? So, this is the maximum interstitial space. Radius is this one. This is like, let us take here, okay, A minus root 3A by 2, okay, into 1 by 2. This is the radius. In terms of A, this is. Sometimes in terms of R also they will ask you. Let us take a question now. See here, let us take a question here. The maximum interstitial space between two edge iron atoms of an atomic radius capital R at room temperature. Same question actually, same question only, but in terms of R they are asking. Now let us say we will solve this question. Now at room temperature, remember at room temperature, okay, the structure of iron is at room temperature, the structure of iron is 4R, the structure of iron is BCC. The structure of iron is BCC at room temperature. The structure of iron is BCC, and BCC follows, BCC what it follows? BCC follows 4R equal to root 3A. 4R equal to root 3 at room temperature, it follows 4R equal to root 3A, right. Now listen, the maximum interstitial space that is equal to, from this diagram, A minus 2R, right, A minus 2R, but in the question in terms of R they want, so that A equal to 4R by root 3, right, so that is 4R by root 3 minus 2R. Now take 2R is a common, 2R into, okay, that is here 2 by root 3 minus 1. This is actually a maximum interstitial space. But in the question, so what they are asking? Maximum interstitial space, right? So maximum interstitial, they are not asking radius, right? So maximum interstitial space is 2R into 2 by root 3 minus 1. So this is the correct answer for this question. So this type of questions they will ask you for your exam, right? The next another important thing I'll explain, listen carefully. At this left side corner, 100% of iron, 0% of carbon. Now what we are doing? We are adding carbon to the iron, and I said the carbon atom is occupying at interstitial space, right? We are adding carbon to the iron and the carbon atom is occupying at interstitial space. Now after occupying, how it is making bond with iron? What type of bond and what type of material is forming, that I am going to explain. Now see here, okay, in an iron carbon alloy, every interstitial carbon atom make bond with 3 iron atoms and form 3 covalent bonds, okay. Let us say here, let us consider here, this is one iron atom, this is another iron atom, this is another iron atom, 3 iron atoms, okay. the carbon atom is making bond with 3 iron atoms like this. This is a carbon atom and form 3 strong covalent bonds here and form 3 strong covalent bonds and form a cementite. This is nothing but a cementite, that is Fe3C, that is nothing but a cementite. It is also known as iron carbide. Iron carbide. Okay. Okay. So, the microstructure of the cementite at 25 micrometer magnification, see this is the cementite microstructure actually. Thin lamellar forms of cementite is present. Surrounded by that there is a ferrite, it is a pearlite structure actually. That black color one represents a cementite. So, what is cementite? Cementite is one phase of iron carbon alloy. And the cementite is a strong, cementite is formed by strong covalent bonds. So, it is the hard material, high strength material, okay, hard and high strength material. And the crystal structure of cementite, remember the structure of the cementite is, remember the structure of cementite is complex orthorhombic structure. Name you should remember, complex orthorhombic structure. Complex orthorhombic structure. And if you consider the properties of the cementite, if you consider properties of cementite, if you consider, it is a hard and brittle material. It is hard and brittle material. Okay, remember these things. Okay, cementite is nothing but iron carbide. Okay, now listen here. Now here, this is 0% of carbon. That means there is a 0% of cementite. 100% of iron is present. Okay, 0% of carbon means no cementite, only iron. Now I am adding carbon to the iron. So carbon atom occupying at interstitial position. So maximum, how much amount of carbon is absorbed by the iron, do you know? That is actually 6.67% of carbon. 6.67% of carbon. Weight percent of carbon. At 6.67 weight percent of carbon, all interstitial spaces are filled. At a 6.67% of carbon, all interstitial spaces are filled. So, the maximum solubility of carbon in iron is 6.67, very, very important. Okay. The maximum solubility of carbon, remember, maximum solubility of carbon maximum solubility of carbon in iron is 6.67 weight percentage. Remember, very, very important. In case if we add carbon more than 6.67, the carbon atoms are going to occupy on the surface of cementite as a graphite. That is why we should not consider more than 6.67. Now, see here, at 0% of carbon, no cementite. Now I am increasing percent of carbon. So cementite formation increasing. The cementite formation increasing, pure form of iron decreasing. At 6.67% of carbon, 100% of cementite is formed and 0% of iron. Now see here, 100% of iron, 0% of cementite. Here 0% of iron, 100% of cementite. That is why this phase diagram is a iron cementite phase diagram. Understand what type of diagram is it is? iron cementite phase diagram. This phase diagram is a iron cementite phase diagram. Cementite is one phase. It's not an iron carbon phase diagram. It's an iron cementite equilibrium phase diagram. Understand now? Right. Now, is it is iron carbon phase diagram or iron cementite phase diagram? Most of you people got doubt. So, I explained from this, it is not an iron carbon phase diagram, it is iron cementite phase diagram. Okay. Next. Again, based on percentage of carbon, listen, based on percentage of carbon, the iron carbon alloys are two types. Okay. Based on percentage of carbon, the iron carbon alloys are two types. Okay. Here it is 2.1% of carbon, that is 6.67, this is 0. Actually, this line is not in touch with the vertical line, line is in touch with the horizontal sleeping line. Here the percentage of carbon is exactly 0.008% of carbon. Now, based on percentage of carbon, the iron carbon alloys are two types. One is steel. The percentage of carbon in steel, the percentage of carbon in steel is 0.008 percentage to 2.1. Second one is a cast iron, that is the percentage of carbon is 2.1 to 6.67. This is a cast iron. This is steel and this is cast iron. Oh, okay now. So, now see here, this is steel actually. This is actually a steel. Okay. This is actually a steel gear, and this is actually a cast iron gear. The surface finish of cast iron is not good because of graphite present in it. It's a steel gear, right. So, now see here, what is steel? Steel is an iron carbon alloy with the carbon percentage that is actually varying from 0.008 percentage to 2.1 percentage. And what is cast iron? Percentage of carbon is varying from 2.1 percentage to 6.67 percentage. Very, very important, you should remember this one. Do you know? Okay. Most of you people think that if general basic question as a mechanical engineer you should remember. So, what type of questions they will ask, you know? What is steel? This type of question. Most of you people think that steel is an iron carbon alloy. That's it, they will give that only. Cast iron is also iron carbon alloy, but percentage of carbon you should mention. Some of you people will say that steel is an iron carbon alloy with the carbon percentage 0 to 2.1. It's not correct actually. 0% of carbon is not a steel. 0% of carbon is nothing but a pure iron. It's not an alloy. So, the minimum percentage of carbon in a steel is 0.008 percentage, maximum is up to 2.1. Cast iron is 2.1 to 6.67 weight percentage, very, very important. Next, let us take a question for IAS question. This is actually IAS question. Statement 1, this is assertion reason question. Statement 1, steel is an interstitial alloy of iron and carbon up to 4.2% of carbon. Those people who do not know what is steel and what is the percentage of carbon in steel, they will think that it is the right statement, but I am saying that it is not right actually, because here it is given 4.2% of carbon. It is not 4.2, it is 2.1% of carbon should be there. It should be 2.1% of carbon. So, this statement is not correct. By default, if the first statement is not correct and second statement always right, so the answer for this question is D. Yesterday I gave the options also. Option A represent the statement 1 and statement 2 are both are correct, and statement 2 is the correct explanation for statement 1. Option B, statement 1 and 2 are correct, but statement 2 is not the correct explanation for statement 1. Option C, statement 1 is correct but statement 2 is not correct. And option D, statement 1 is not correct but statement 2 is correct. Right. So, here statement 1 is not correct, it is incorrect, statement 2 always a correct. Okay. So, interstitial alloy is formed by adding solute at interstitial positions of solvent, it is right. So, the answer for this question is D. Okay. The answer for this question is D. Next. So, that is the information about x-axis. Now, next I am going to discuss about y-axis. The y-axis represent temperature, right. Now, listen, if we cool the liquid material from liquid state, let us consider, I will take only this portion of the diagram, I will take only this portion of the diagram. Okay. If we cool the material only from liquid state, if we cool the material from liquid state actually, okay, like that, if we cool the material from the liquid state, listen carefully, this is, let us consider liquid. By cooling the liquid material at this line, solidification starts. So, liquid plus delta iron, this is a delta iron, this is delta plus gamma, this is a gamma iron, this is alpha plus gamma, this is alpha plus cementite, right. This is the representation of phases. Okay. So, from the liquid state, if we cool, initially delta iron is formed, and the crystal structure of this delta iron is actually BCC structure. The crystal structure of this delta iron is actually BCC structure, and after that gamma iron is formed. The crystal structure of gamma iron is FCC structure. Again, by cooling, that gamma iron transforms into alpha iron, and the crystal structure of this alpha iron is BCC. So, this is an allotropy of iron. So, what do you mean by allotropy of iron? The iron material exhibits different crystal structures with different temperatures. Okay. Allotropy means different crystal structures with different temperature. Remember, different crystal structure, different crystal structures of same metal but different temperatures. Different crystal structure of same metal but different temperatures. This is allotropy of iron. This is allotropy of iron. Okay. Delta iron BCC, gamma iron FCC, alpha iron is again BCC. Now, see here, I gave a chart here. If you observe carefully, the delta iron is BCC structure, the gamma iron is FCC structure, and alpha iron is again a BCC structure. Alpha iron again a BCC structure. This is very, very important for your exam. Remember, this is very, very important. Delta iron is a BCC structure. Gamma iron, it is also known as austenite. Okay, it is also known as austenite. Its structure is FCC. This question asked in GATE 2022 this year. And alpha iron, that we can say ferrite. Okay, its structure is again a BCC structure. And a cementite is orthorhombic structure. You should remember these structures, very, very important for your exam. See, one of the question, previous year GATE question, match the following question. In the list 1, type of iron is given, and in the list 2, crystal structures are given, right. So, here alpha iron, the crystal structure of the alpha iron is a BCC structure, and the crystal structure of austenite is FCC structure. The gamma iron crystal structure is again, sorry, it's a delta iron, we can say it's a delta iron, again it's a BCC structure, and the cementite structure is actually orthorhombic structure. Okay. So A is 2, B is 3, C is again 2, D is 1. So the most appropriate answer for this question is C. 2, 3, 2, 1. 2, 3, 2, 1. The correct answer for this question is C, right? Now, second, another important thing is iron is a magnet or not? Most of you people are in confusion with this concept actually. Is it iron is a magnet or not? First of all, remember, a fresh and pure form of iron is not a magnet, it's a magnetic material. In case if you apply the magnetic field to a iron piece, it will become magnetized. Okay. Remember, okay, the iron is a good ferromagnetic material. Remember, iron is a ferromagnetic material. Iron is a ferromagnetic material. Ferromagnetic material. Ferromagnetic material. Now, listen carefully. What is this ferromagnetic material? I'll explain elaboratively here. In every iron metal, there is a permanent dipoles. Okay, this is a fresh iron metal, means fresh iron metal means it is not affected by any magnetic field. H is magnetic field. Magnetic field is 0. Okay, it's a fresh iron metal I am taking. It's a fresh iron metal. Fresh iron piece I am taking, it is not affected by any magnetic field. So without any magnetic field, in this iron piece, the dipoles are present, permanent dipoles are present, but these dipoles are randomly oriented. There is no proper order like this. That's why it is not showing any magnetic power. The iron piece, if you see that one, that is not a magnet actually. That is not a magnet actually. But in case if you apply the magnetic field to the iron metal, let us take H, I am applying, H is not 0, I am applying the magnetic field in this direction. Let us take, I am applying the magnetic field in this direction. So by applying magnetic field in this direction, see here, the magnetic dipoles, all the magnetic dipoles are aligned in the direction of the field. All the magnetic dipoles are aligned in the direction of the field and generate large intensity of magnetization. This is a ferromagnetic behavior. So the iron metal is a good ferromagnetic material and it generates very large intensity of magnetization. That's why this iron metal we are using in electronic components like transformer core we are using. Right, understand clearly, transformer core we are using because it's a very good ferromagnetic material. Right. But one important thing you should remember, that is actually the ferromagnetic material depends on temperature actually. Depends on, the ferromagnetic material depends on temperature. Depends on temperature. Now listen, with increasing temperature, the intensity of magnetization is decreasing. With increasing temperature of this iron metal, due to the lattice vibrations, whatever the aligned dipoles are going to be disturbed, randomized, and it convert into a paramagnetic material. Exactly at one point of temperature, it convert into a paramagnetic material, that is nothing but a Curie point of temperature. For your exam point of view, you should remember that Curie point of temperature. Here I am giving that Curie point of temperature, that is actually 768 degrees Celsius. Okay. Remember, this is very important. Curie. Remember, this is very, very important. Okay. Curie temperature of iron. Curie temperature of iron. Curie temperature of iron is 768 degree Celsius, or otherwise in terms of Kelvin, remember, very, very important, 1041 Kelvin. Okay, the Curie temperature of iron is 768 degree Celsius or 1041 Kelvin. At this point of temperature or above this point of temperature, the ferromagnetic material convert into ferromagnetic material convert into a paramagnetic material. At this Curie point of temperature, the ferromagnetic material convert into a paramagnetic material. Remember, very, very important. At Curie temperature, ferromagnetic material convert into paramagnetic material. Now listen. There is alpha iron, gamma iron, delta iron, but you may get doubt, sir, where is beta iron, like that? You may get doubt. Listen, it's a very simple. From room temperature to 768 degrees Celsius, listen carefully, from room temperature to 768 degrees Celsius, the alpha iron is a ferromagnetic alpha iron. The alpha iron is a ferromagnetic alpha iron, and from 768 degrees Celsius to 910 degrees Celsius, the alpha iron is a paramagnetic alpha iron. This paramagnetic alpha iron is nothing but a beta iron. Okay, very, very important, remember. Okay, you may get doubt in interview, they will ask you, beta iron is nothing but an alpha iron, that is actually a non-magnetic alpha iron. Paramagnetic alpha ferrite from 768 degrees Celsius to 910 degrees Celsius is nothing but a beta iron. From 768 degrees Celsius to 910 degrees Celsius is nothing but a beta iron. Okay, now, right. Now, there is a question actually, see here, this type of questions also sometimes they will ask you. The Curie temperature of iron, above that ferromagnetic material transforms into paramagnetic. I said at a 768 degrees Celsius it is transforms into para. But most of you people they will remember this answer and they will try to give this 768. But it is not correct, because it is actually in the question it is given in terms of Kelvin. So 768 plus 273 will get 1041. So this is the correct answer, you should remember. Be careful. In case in terms of Celsius, if it is given, that the answer is 768 degrees Celsius, otherwise it is 1041 Kelvin. Right. Next. The number of phases present in iron-cementite phase diagram. Remember, the number of phases present in iron-cementite phase diagram, if you see here, the number of phases present in iron-cementite phase diagram, if you see the diagram here, okay, let us take the reference diagram, maybe it is not visible properly here. This is actually a delta iron, one phase, solid phase. This is a gamma iron, another phase. This is a alpha iron, another phase here, and this is a cementite. Okay, right. So there are 4 solid phases and 1 liquid phase is present. Now I'll write these points here. The number of phases present in iron-cementite phase diagram here. Remember, there are 5 phases. Okay, remember 5 phases are there. 5 phases are there. One is actually a liquid. Second is delta ferrite. second is delta ferrite, third is austenite, that is nothing but a gamma iron, fourth is alpha ferrite or alpha iron, and fifth is cementite. You should remember all these phases. Fifth is cementite, alpha iron, delta iron, austenite, okay, cementite. Now let us see here the percentage of carbons. If I consider, the maximum solubility of carbon in delta iron is up to 0.09% of carbon. In austenite, the percentage of carbon is up to 2.1. From the diagram you will get to know that one. Alpha iron, the percentage of carbon is actually 0.025 or 2% of carbon, and cementite, the maximum solubility of carbon is 6.67% of carbon. You should remember this percentage of carbons also. Okay now. Next, another important concept from this iron cementite phase diagram, that is actually equilibrium reactions. Equilibrium reactions. The equilibrium reactions are also known as invariant reactions. Equilibrium reactions are also known as invariant reactions. Invariant reactions. Invariant reactions or reversible reactions. Right. So one by one I will explain these reactions here. First reaction is eutectic reaction. What this eutectic reaction represent? Eutectic reaction represent a liquid upon cooling, okay, or otherwise upon heating, two different solids are going to be formed, solid 1 and solid 2. Liquid upon cooling transforms into two solids, otherwise two solids upon heating transforms into a liquid. You should remember this reaction. This reaction is very, very important for your exam. Actually, this reaction is present in iron cementite phase diagram at 4.2% of carbon. If you see the diagram here, at this point this reaction takes place. See here, at this point here, above this material is liquid, below this there are two solid phases, gamma iron plus cementite. The percentage of carbon here, it is actually 4.2% of carbon and some 1100 degrees Celsius. Okay, that I am writing here, the reaction I am writing here. Okay, see here, a liquid at 4.2% of carbon and 1100 degrees Celsius transforms into gamma iron plus cementite. Gamma iron plus cementite. This reaction you should remember for your exam. Next, the second reaction is eutectoid reaction. Okay, you should remember the definition of eutectoid reaction. What is eutectoid reaction actually? A solid, one solid upon cooling transforms into two different solid phases, solid 2 and solid 3. Otherwise, two solids upon heating transforms into another solid. This reaction actually is present in iron cementite phase diagram at a 0.8% of carbon. Gamma iron upon cooling at 0.8% of carbon and 728 degrees Celsius or 727 degrees Celsius transforms into alpha iron plus cementite. Alpha iron plus cementite. Okay, this is at 0.8% of carbon takes place, that's why it is related to steel, and this is related to cast iron. And finally, the last one more reaction, that is a peritectic reaction. The peritectic reaction is nothing but a liquid plus one solid, liquid plus one solid upon cooling transforms into a different solid phase. Otherwise, liquid plus one solid upon heating transforms into a liquid. This reaction actually takes place at a very high temperature, that is actually 1450 degrees Celsius, and at 0.18% of carbon, okay, that is actually a liquid plus, okay, liquid plus delta iron upon cooling at 0.18% of carbon and 1450 degrees Celsius transforms into a gamma iron, right. So this is the peritectic reaction. So remember, in an iron cementite phase diagram, only three equilibrium reactions are present: eutectic, eutectoid, peritectic. There is no peritectoid reaction, very, very important thing. So this is the complete theoretical information about the iron cementite phase diagram. So from this concept, there are so many questions they will ask you for your exam. Okay, that's why I selected this topic and I explained most of the things in within this 1 hour. Okay, right, and thanks for listening my video. All the best for your exam.